Hello there and welcome back to the Science Sleepy Minds. Picture this. You're standing in your backyard right now, barefoot on cool grass, neck craned so far back you can feel the vertebrae gently popping. Above you, the sky is doing that thing it does on a clear night, showing off. Thousands of tiny white pinpricks scattered across a velvet canvas so dark it almost feels heavy. Your eyes drift across constellations you half remember from a school project, past the pale river of the Milky Way, and land on one particular dot. It looks ordinary, unremarkable even, but that little flicker of light left its home star system roughly 4 years and 4 months ago, travelling at the fastest speed the universe allows, and it is only just now tapping your retina like a polite knock on a door. That star, or more accurately that star system, is Alpha Centauri, our nearest stellar neighbour, and tonight you and I are going to talk about just how far away it really is. Spoiler, you probably will not survive the trip. Nobody alive today will. Possibly nobody alive in the next several centuries will either, but that has never stopped humans from dreaming, and it certainly will not stop us from talking about it in soothing tones until you fall asleep. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop a comment with where you are listening from and what time it is there. I always love reading those. Someone last week was tuning in from a fishing boat off the coast of Norway at 3 in the morning, and honestly, that is the exact energy this channel thrives on. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You tilt your head back again. That dot, Alpha Centauri. The name itself carries a certain weight, does it not? It sounds like something a Roman general would name his favourite horse, and in a way the name does trace back to antiquity. The ancient Greeks catalogued it, the ancient Egyptians likely used it for navigation, and the Arabic astronomers who bridged the classical and medieval worlds gave many of its companion stars the names we still use today. Alpha Centauri sits in the constellation Centaurus, the centaur, which the Greeks associated with Chiron, the wise immortal centaur who tutored Achilles and Heracles. There is a fun irony there. Chiron was famous for being the one mythological creature who actually wanted to die, who eventually traded his immortality to free Prometheus from his chains, and here we are, mortal beings, staring at a star named after him, wishing we had enough lifespan to reach it. The mythology practically writes its own punchline. Now here is the thing that most people get wrong about Alpha Centauri, and I mean this with love, because I got it wrong for years too. When you look up at that dot, you're not looking at one star, you're looking at a system, a little family of stars gravitationally bound, doing their thing together in a quiet corner of the Milky Way roughly 4.37 light years from your eyeballs. But from Earth, with the naked eye, it looks like a single point. It is like seeing a house from an airplane and assuming only one person lives there. Historians still argue whether some ancient civilizations, particularly the Aboriginal Australians whose astronomical traditions stretch back tens of thousands of years, recognized the binary nature of the system before European telescopes split the light. Some oral traditions from indigenous Australian groups describe the Alpha Centauri system as 2 distinct campfires, which, if true, means they figured it out with nothing but extraordinary eyesight and patience. No lenses, no instruments, just human eyes doing what human eyes were apparently always capable of if you paid enough attention. Meanwhile, European astronomy did not confirm the binary nature until 1689, when a Jesuit priest named Jean Richaud pointed a telescope at the system from Puducherry, India, and went, effectively, "Oh, there are 2 of them." That quirky little historical footnote aside, You settle deeper into whatever surface is currently holding you. A bed, a couch, a beanbag, the back seat of a car, I do not judge. And you let the scale of this start to sink in. 4.37 light years. That is the distance. It sounds almost manageable, does it not? Single digits. You could count to 4 on one hand. But a light year is not a unit of time, despite the word year being right there. Misleading everyone since the term was coined. A light year is a unit of distance, and it is a monstrous one. 1 light year is approximately 9.461 trillion kilometers. Let that number breathe for a moment. Trillion. With a T, that is 12 zeros, and you need 4.37 of those. So the total distance from here to Alpha Centauri is roughly 41.34 trillion kilometers. Written out, that is 41,340 billion kilometers. Your car's odometer would need to be redesigned by a team of engineers who specialize in existential dread. And yet, and this is the part that keeps astronomers up at night and also, paradoxically, the part that should help you sleep, Alpha Centauri is the closest one, the nearest star system to our own. In cosmic terms, it is the neighbour whose fence touches yours. If the Milky Way galaxy were a city, Alpha Centauri would be the apartment next door, and you could theoretically hear them playing music through the wall. But in human terms, in the terms of flesh and bone and rocket fuel and limited budgets, it might as well be on the other side of the observable universe. That gap between how close it is cosmically and how far it is practically is the central tension of everything we're going to talk about tonight. It is the reason this topic keeps scientists awake, and, with any luck, the reason it will put you to sleep. You breathe out slowly. The grass is cool beneath your shoulders. The stars are indifferent to your gaze as they have always been. And you are about to learn exactly how indifferent they are, measured in every unit of distance and speed and time that the human mind has ever invented. So let your body sink a little heavier, let the night air settle around you, and let us begin. So you know it is out there. You know it is 4.37 light years away. But what exactly is Alpha Centauri? You've heard the name tossed around in science fiction like a casual destination. Characters in novels and films hop over to Alpha Centauri the way you might drive to the next town for groceries. But no one ever stops to describe the place. And honestly, the reality is stranger and more beautiful than most fiction gives it credit for. Alpha Centauri is a triple star system, 3 stars bound together by gravity, doing an elaborate celestial dance that has been going on for roughly 6 billion years. The 2 main stars are Alpha Centauri A and Alpha Centauri B, creative names, I know, really pushing the boundaries of astronomical poetry there. And they orbit each other in a pattern that takes about 79.9 years to complete one full loop. Alpha Centauri A is the bigger sibling. It is a G-type main sequence star, which in plain language means it is almost eerily similar to our own Sun. Slightly more massive, slightly more luminous, roughly the same surface temperature. If you were standing on a hypothetical planet orbiting Alpha Centauri A at the right distance, the light warming your face would feel remarkably familiar. You might even get a tan that looks the same. You would not know, just from the sunlight alone, that you were 41 trillion kilometers from home. Alpha Centauri B is the younger-looking sibling who still gets carded at bars. It is a K-type star, which means it is smaller, cooler, and dimmer than A, but still respectable in its own right. It puts out roughly half the luminosity of our Sun. If A is a bright desk lamp, B is a nice warm reading light, the kind you would use for exactly this sort of late-night listening session. Together, they form what astronomers call a binary pair, and their orbit is not a perfect circle, but an ellipse that brings them as close as 11.2 astronomical units to each other, roughly the distance between the Sun and Saturn, and swings them as far apart as 35.6 astronomical units, which is nearly the distance from the Sun to Pluto. So from the perspective of any planet in that system, you would sometimes see two bright suns in your sky, and other times one would be merely a very brilliant star hovering near the horizon. Imagine the sunsets. Imagine the confusion of ancient civilizations on that world, trying to build calendars around that double rhythm of light. And then there is the third member of the family, Proxima Centauri, the runt, the odd one out, the little red dwarf star that sits so far from the other two, about 12,950 astronomical units away, or roughly 0.2 light years, that astronomers spent decades debating whether it is actually gravitationally bound to the system at all, or just passing through the neighbourhood on its own long, lonely trajectory. Recent measurements, particularly from the European Space Agency's Gaia mission, which has been mapping the positions and motions of over 1 billion stars with extraordinary precision, suggest that Proxima is indeed bound to the system. It is orbiting A and B, but on an orbit so vast and so slow that one trip takes somewhere around 547,000 years. To put that in perspective, 547,000 years ago, Homo sapiens did not yet exist. Neanderthals were still figuring things out. Proxima started its current orbit before our species was born, and it will not finish that orbit until long after whatever we become has either spread across the galaxy or gone extinct. Historians still argue whether Proxima should be considered a true companion or a captured interloper, a star that wandered too close and got trapped by gravity. The evidence leans toward genuine family membership, but the debate simmers on, the way family arguments about who is actually invited to Thanksgiving tend to simmer. Here is a quirky little detail that often gets overlooked. Proxima Centauri, despite being part of the closest star system to us, was not discovered until 1915. Alpha Centauri A and B have been observed since antiquity. The system is one of the brightest objects in the southern sky, easily visible from anywhere below about 29 degrees north latitude. But Proxima is so faint, so small, and so far from the bright pair that it took a Scottish astronomer named Robert Innes, working at the Union Observatory in Johannesburg, South Africa, to spot it. He noticed a faint star that shared the same proper motion, the same apparent drift across the sky as Alpha Centauri, and he realized it must be physically associated. He named it Proxima, from the Latin for nearest, because at the time of its discovery it was recognized as the closest known star to our Sun, and it still holds that title over a century later. Proxima Centauri is approximately 4.2465 light-years away, making it just a hair closer than its two brighter companions. It is the front porch of the nearest house. But do not let that modest distance fool you into thinking Proxima is a gentle star. Red dwarfs are notoriously moody. Proxima Centauri is what is known as a flare star, meaning it periodically erupts with violent bursts of radiation that can double or even triple its brightness in minutes. In 2016, astronomers detected a superflare from Proxima that was roughly 10 times more energetic than the strongest solar flare ever recorded from our own Sun. If you were standing on a planet near Proxima, which, as we will discuss later, you theoretically could be, that flare would have been like getting a surprise full-body X-ray you did not consent to. The star basically throws tantrums, and any planet close enough to be in the habitable zone is close enough to get scorched during those tantrums. It is the cosmic equivalent of living next to a neighbour who is lovely 99% of the time but occasionally sets off fireworks inside the house. You lie there, staring up, and you try to picture it. Two bright stars waltzing in elliptical elegance, taking 80 years to complete a single dance. A tiny red dwarf lurking at the edge, flickering with rage, and all of it, all three stars and whatever planets circle them, sitting at a distance so vast that the light telling you about their existence is already old news by the time it arrives. It is a family portrait taken 4.37 years ago. Whatever is happening there right now, right this very second as you lie here, you will not know about it until years from now. And that is just for the photons, for anything with actual mass, a spacecraft, a message in a bottle, you. The commute is so much worse, but that, as they say, is a problem for the next few breaths. The first problem, of course, is measuring the distance in the first place. You cannot exactly stretch a tape measure from here to Alpha Centauri, and for most of human history, the distance to the stars was filed under very, very far and left politely at that. The ancient Greeks had some ideas. Aristarchus of Samos, around the 3rd century BCE, correctly proposed that the sun was much larger than the Earth and that the stars were incredibly distant suns. But his contemporaries mostly ignored him because the idea was uncomfortable, and also because Aristotle had said otherwise, and disagreeing with Aristotle in ancient Greece was a bit like disagreeing with the internet today. You could do it, but you would be loudly and persistently told you were wrong by people who had not actually checked for themselves. The real breakthrough came from a technique that sounds deceptively simple: parallax. You know how if you hold your thumb out at arm's length and close one eye, then switch eyes, your thumb appears to jump against the background. That jump is parallax, the apparent shift in an object's position caused by looking at it from two different viewpoints. Now scale that up enormously. Instead of your two eyes, use the Earth at two opposite points in its orbit around the Sun, say January and July. That gives you a baseline of about 300 million kilometers, which is as long a ruler as our solar system conveniently provides. If a nearby star shifts its apparent position against the background of much more distant stars when viewed from these 2 points, you can measure that shift, the parallax angle, and use basic trigonometry to calculate the distance. The smaller the angle, the farther the star. Simple in principle, nightmarish in practice. The concept was understood as far back as the 16th century. Copernicus himself knew that if the Earth really moved around the Sun, stellar parallax should be observable. The fact that nobody could detect it was actually used as an argument against heliocentrism. If the Earth moves, the critics said, the stars should appear to shift. They do not shift, therefore the Earth does not move. The logic was perfectly sound. The assumption was wrong. The stars did shift. The shift was just so incomprehensibly tiny that no instrument of the era could detect it. It's like trying to measure the width of a human hair from a kilometre away using a wooden ruler. You're not wrong to try. You just need much, much better tools. And the tools would not arrive for another 300 years, which in the history of science is practically a coffee break, but in human lifetimes is an eternity. Those better tools arrived in the 19th century. In 1838, 3 astronomers independently raced to become the first to successfully measure stellar parallax. Friedrich Bessel, a German astronomer working at the Königsberg Observatory, won the race by measuring the parallax of the star 61 Cygni. His measurement placed the star at about 10.3 light-years away, and he was remarkably close to the modern value of 11.4 light-years. Around the same time, Thomas Henderson, a Scottish astronomer working at the Royal Observatory at the Cape of Good Hope in South Africa, measured the parallax of Alpha Centauri. His result indicated that Alpha Centauri was roughly 3.25 light-years away, off by about a light-year from the true value, but still a stunning achievement given the tools he had. Historians still argue whether Henderson actually completed his calculations before Bessel, but delayed publication because he doubted his own results. If true, that is one of the most painfully relatable moments in the history of science. Imagine being the first person to measure the distance to the nearest star and thinking, "Nah, that cannot be right. Better sit on this for a while." The third contender, Friedrich Georg Wilhelm von Struve, measured the parallax of Vega and got a result that was, charitably, in the right ballpark. The 1830s were a thrilling time to be an astronomer with a good telescope and a tolerance for tedium. The parallax angle for Alpha Centauri is about 0.742 arcseconds. To put that in perspective, 1 arcsecond is 1/3600th of a degree. The full moon spans about 1,800 arcseconds across your sky. So the parallax shift of our nearest stellar neighbour is roughly 2,400 times smaller than the apparent diameter of the moon. You're trying to detect a wobble so small that if it were a physical distance at arm's length, it would be thinner than a strand of spider silk. And yet, with increasingly precise instruments, astronomers nailed it. The European Space Agency's Hippocos satellite, launched in 1989, measured the parallax of Alpha Centauri with enough accuracy to pin down the distance to within a fraction of a percent. And then Gaia, Hippocos' spectacularly capable successor, launched in 2013, refined it even further. Gaia can measure parallax angles as small as a few micro-arcseconds, which is like detecting the width of a coin sitting on the surface of the moon from your backyard on Earth. It is measuring so precisely that it has to account for the bending of light by our own sun's gravity. Einstein's general relativity literally warps the measurements and has to be mathematically subtracted out before the data makes sense. So the answer, after centuries of squinting and calculating and launching satellites, is 4.37 light-years. Give or take a cosmic whisker, the confidence is high, the distance is known, and knowing it precisely, it turns out, only makes the existential weight heavier, because now you cannot hide behind uncertainty. You cannot say, well, maybe it is closer than we think. It is not. It is 4.37 light-years, and the number is firm, and in the next breath, you're going to start understanding what that number actually feels like, which is the part where most people's brains quietly file a complaint with the management. You shift on the grass. A breeze moves through, carrying the scent of something floral and nighttime, and you think about Thomas Henderson sitting in his observatory in South Africa in the 1830s, squinting through an eyepiece, watching Alpha Centauri drift by fractions of a degree, and wondering if he was witnessing a real measurement or an instrumental error. The courage it takes to trust a number that small. The discipline to look at something that far away and say, I know how far that is, and I can prove it. Meanwhile, you're lying here struggling to estimate how far the nearest gas station is without opening your phone. The gap between human intuition and human achievement has never been wider, and somehow that thought is both humbling and deeply comforting as you settle further into the dark. Now you know the distance, 4.37 light-years, 41.34 trillion kilometers. But those numbers are so large they slide off the brain like water off a duck. Your mind was not built for trillions. It was built for counting predators, estimating the distance to the nearest fruit tree, and judging whether that shadow in the tall grass was a lion or a rock. trillions were not part of the evolutionary curriculum. So let us do what every good science communicator does when the numbers get absurd. Let us shrink things down until the absurdity fits inside your skull. Imagine the sun is a bowling ball, a standard 10-pin bowling ball, about 22 centimeters in diameter. You place it on the ground in an open field. At that scale, the Earth would be a tiny peppercorn, about 2 millimeters across, sitting roughly 23 meters away. That is about the length of a large swimming pool. You could walk from the sun to Earth in less than 30 seconds at a normal pace. Jupiter, the big bully of the solar system, would be a marble about 2.3 centimeters in diameter, sitting about 120 meters from the bowling ball. Neptune, the most distant planet, would be a small bead roughly 750 meters away. So the entire solar system, from the bowling ball sun to the bead Neptune, fits comfortably within a kilometer or so. You could walk the entire span during a lunch break. Now, where is Alpha Centauri on this scale? You might expect it to be across town, maybe across the city, perhaps in the next state or province. It is not any of those. On this scale, where the sun is a bowling ball and the Earth is a peppercorn 23 meters away, Alpha Centauri A would be another bowling ball, almost identical in size, sitting approximately 6,200 kilometers away. That is roughly the distance from New York to London, or from Tokyo to Mumbai, or from Cape Town to Cairo. You have shrunk the sun to something you can hold in one hand, and the nearest star is still an intercontinental flight away. Let that settle. Let it really percolate into whatever part of your brain handles spatial reasoning, and notice how that part quietly gives up and requests a transfer to a less demanding department. There's another way to think about it that might land differently. The International Astronomical Union defines one astronomical unit, 1 AU, as the average distance from Earth to the Sun, about 150 million kilometers. Alpha Centauri is roughly 276,000 astronomical units away. So if you could somehow drive from the Earth to the Sun, which would itself take a laughably long time at highway speed, you would need to do that same drive 276,000 more times to reach Alpha Centauri. If each drive took 2 years at highway speed, and it would take much longer than that, but let us be generous, you would be driving for over 500,000 years. Your car would not just need an oil change, it would need to be reinvented from scratch multiple times over as civilizations rose and fell around you. Languages were born and died. An entire species evolved and went extinct while you were still on the road. Here is a fun one that physicists like to trot out at parties, if physicists went to parties, which is a debate for another time. The Voyager 1 spacecraft, currently the most distant human-made object from Earth, is travelling at roughly 17 kilometers per second relative to the Sun. At that speed, it would take approximately 73,000 years to reach Alpha Centauri, if it were heading in that direction, which it is not. 73,000 years. For reference, 73,000 years ago, modern humans had barely begun leaving Africa. We had not yet invented agriculture, writing, cities, or the concept of a weekend. The entirety of recorded human history, every empire, every war, every invention, every terrible reality television show, fits inside about 5,000 years. Voyager would need 14 times that much time. You would need to replay all of human civilization from the first clay tablet to this very moment 14 times over, back to back, and Voyager still would not have arrived. It would probably still be somewhere in the middle, complaining about the Wi-Fi and wondering if anyone was still listening. Scholars and science communicators have been struggling with this scale problem for decades. In 1977, Charles and Ray Eames created a famous short film called Powers of 10 that attempted to illustrate the vast differences in scale across the universe by zooming out from a picnic in Chicago to the edges of the observable cosmos. It remains one of the most effective visualizations ever made, and even it struggles to convey the gap between our solar system and the next star. The jump from local to interstellar is where human brains tend to politely check out. Historians still argue whether our inability to intuitively grasp cosmic distances is a failure of education or simply a fundamental limitation of a brain that evolved to navigate African savannas, not the voids between stars. And here is a quirky tidbit that might make you smile as you drift. In 1998, a Swedish project called the Sweden Solar System created the world's largest scale model of the solar system. The Sun is represented by the Ericsson Globe Arena in Stockholm, a spherical building 110 meters in diameter. The planets are scattered across Sweden at proportional distances. Pluto sits at the Delsbo switching station, 300 kilometers from Stockholm. On this scale, where would Alpha Centauri be? Some estimates place the equivalent distance somewhere near the actual orbit of the Moon, roughly 384,000 kilometers away. You build the largest model solar system on the planet, stretching across an entire country, and the nearest star is still so far away that you would have to leave Earth entirely to place it. That is the kind of cosmic joke that would make even Chiron, the wise centaur from our first section, shake his head and walk back into his cave. You close your eyes for a moment just to let the scale soak in. The air is warm. The distant hum of whatever city or countryside surrounds you has faded into white noise. And somewhere in your mind, a small voice is whispering, "If it is this far away, why do we even bother looking? Why do we build telescopes and send probes and dream about crossing the void?" You know the answer, of course. You have always known it. But for now, you let the question float, unanswered, like a leaf on still water. The speed of light. It sounds majestic when you say it out loud. 300,000 kilometers per second. A beam of light leaves the sun, and in 8 minutes and 20 seconds it is warming your face. It bounces off the Moon and reaches your eyes in 1.3 seconds. It crosses the entire diameter of Earth's orbit in about 16 minutes. Light is, by any reasonable human standard, preposterously fast. It is the Usain Bolt of the universe, except it never slows down, never tires, and never retires to do endorsement deals or open a restaurant. And yet, even light, the fastest thing the laws of physics will ever allow, takes 4.37 years to cross the gap between our Sun and Alpha Centauri. If light finds the commute tedious, what hope do the rest of us have? You lie there and you think about that. A photon leaves Alpha Centauri A right now, right this second, as your chest rises and falls. It tears away from the surface of that star at 299,792.458 kilometers per second, which is the exact speed of light in a vacuum, a number so precise that scientists have defined the meter itself in terms of it. That photon hurtles through the interstellar void, dodging nothing because there is almost nothing to dodge, and it arrives at your retina in the year 2030. If you're listening to this in 2026, that photon is currently somewhere around 3/4 of the way here. It has already been travelling for over 3 years and it still has more than a year to go. And this is the fast option. This is the universe's express lane. Everything else, every rocket, every probe, every ambitious plan humanity has ever conceived, is slower. Often laughably so. Einstein figured this out, or more accurately, Einstein figured out why this is the case and why it cannot be otherwise. In 1905, working as a patent clerk in Bern, Switzerland, which is one of those historical facts that should make every person stuck in a boring office job feel a surge of irrational hope, he published his theory of special relativity. The core idea, stripped of the mathematics that makes graduate students weep, is this: the speed of light in a vacuum is the same for every observer, regardless of how fast they are moving. You could be standing still on a sidewalk or flying at half the speed of light in a spaceship, and a beam of light would still pass you at exactly the same speed. This sounds counterintuitive because it is. In everyday life, speeds add. If you throw a ball forward on a moving train, the speeds combine. But light refuses to play by those rules. If you are on a train going at 99% the speed of light and you turn on a flashlight, the light still moves at exactly the speed of light relative to the ground. The universe cheats. It warps time and space themselves to keep that number constant. The consequence of this, the one that matters for our sleepy journey tonight, is that nothing with mass can ever reach the speed of light. As you accelerate, your effective mass increases, and the energy required to accelerate further grows without bound. To push even a single kilogram to the speed of light would require infinite energy. Not a lot of energy. Infinite. The kind that does not and cannot exist. The universe has drawn a line in the sand and said, "This fast, no faster. I do not care how clever you are." This is what makes the distance to Alpha Centauri so terrifying. It is not just that the distance is large, it is that the speed limit is hard. In everyday life, if a destination is far away, you can compensate by going faster. Need to cross a country? Fly instead of drive. Need to cross an ocean? Take a jet instead of a ship. There is always a faster option, a technological leap that compresses distance into convenience. But for interstellar travel, there is no faster option than light, and light itself finds the trip inconveniently long. You're not stuck in traffic. You're stuck in the laws of physics, and there is no alternate route, no shortcut app, no wormhole that has been confirmed to exist in a way that would actually help. Historians still argue about whether Einstein himself fully grasped the implications of special relativity for space travel when he first published it. He was primarily concerned with electrodynamics and the behavior of a light, not with the dream of visiting other stars. But the implications were there from the beginning, lurking in the equations like a footnote that would eventually become the main text of humanity's greatest frustration. By the mid-20th century, as rocketry advanced and the idea of space travel shifted from science fiction to engineering possibility, the speed of light limit became the central heartbreak of interstellar ambition. We could reach the moon, we could reach Mars, we could with patience and clever engineering send probes to the outer planets. But the stars? The stars were behind a wall that no amount of thrust could break through. There is a quirky sidebar here that is worth mentioning as your breathing slows and the night deepens around you. Tachyons. You might have heard the word in a movie or a late-night Wikipedia rabbit hole. Tachyons are hypothetical particles that travel faster than light, not by accelerating past it, but by being born on the other side of the speed limit, permanently unable to slow down below it. They are the mirror image of us. We can never go fast enough, and they can never go slow enough. The concept was formalized in the 1960s by physicist Gerald Feinberg, and for a brief, giddy moment, some people wondered whether tachyons could be used to send messages or even objects faster than light. The answer, as far as current physics can tell, is no. tachyons, if they exist at all, would violate causality. They would allow effects to precede causes, which tends to make the universe's bookkeeping very messy. Most physicists treat them as a mathematical curiosity rather than a real particle, like an imaginary friend that the equations occasionally mention, but no one has ever actually met at a party. So here you are, pinned to the universe's speed limit, staring up at a star system 4.37 light-years away and doing the math in the soft part of your brain. Even at the speed of light, which remember you cannot reach, the trip takes 4.37 years. At any realistic speed, it takes incomprehensibly longer. The cosmic speed limit is not a suggestion, it is a law, and unlike human laws, it cannot be lobbied against, protested, or repealed. It simply is, and you simply are, lying here beneath it, breathing slowly, and letting the weight of that truth settle over you like a second blanket. So light takes 4.37 years. You cannot go that fast. What about the things humanity has actually built and flung into the cosmos? You've probably seen the headlines. Fastest spacecraft ever, probe breaks speed record, and felt a flicker of hope. Surely we are getting faster. Surely if we just keep improving, keep iterating, keep filing those patents, and writing those grant proposals, the stars will come within reach. Let us look at the actual numbers and see how that hope holds up. Spoiler, not well, but the engineering is still beautiful, and beauty counts for something at this hour of the night. Voyager 1 is the obvious starting point. Launched in September 1977, it completed its grand tour of Jupiter and Saturn, sent back some of the most iconic photographs in human history. Those swirling Jovian storms, the rings of Saturn in backlit glory, and then just kept going. It crossed the heliopause, the boundary where the sun's influence gives way to interstellar space, in August 2012, becoming the first human-made object to enter interstellar space. As of right now, it is roughly 24 billion kilometers from Earth, travelling at about 17 kilometers per second relative to the Sun. That is approximately 61,000 kilometers per hour. Fast enough to cross the entire United States in about 4.5 minutes. But pointed at Alpha Centauri, which it is not, it would arrive in roughly 73,000 years. The year 75,026 CE. The Roman Empire fell about 1,500 years ago. Voyager would need you to wait through 48 more collapses of that magnitude before it showed up. You would need to be very, very patient and also immortal, and also not particularly concerned about whether anyone remembered to pack snacks. Voyager 2 is not far behind. Well, actually it is quite far behind, at about 20 billion kilometers out, moving slightly slower. New Horizons, the plucky little spacecraft that gave us our first close-up images of Pluto in 2015, is moving at about 14 kilometers per second, slower than Voyager. Alpha Centauri ETA, roughly 78,000 years. Pioneer 10, launched in 1972, is the granddaddy of deep space probes, crawling along at about 12 kilometers per second. Its Alpha Centauri ETA, if it were aimed correctly, would be around 90,000 years. These are our scouts, our fastest envoys, the sharpest arrows in our quiver, and every single one of them would need longer than recorded civilization has existed to reach the nearest star. Now here is where it gets interesting, because those are not actually our fastest spacecraft. They are just our fastest spacecraft currently heading outward, away from the Sun. The Parker Solar Probe, launched in 2018, holds the record for the fastest human-made object ever. During its close passes to the Sun, using gravity assist to slingshot itself into tighter and faster orbits, it has reached speeds of approximately 192 kilometers per second, over 690,000 kilometers per hour. That is fast enough to travel from New York to Tokyo in under a minute. It is roughly 0.064% of the speed of light, which sounds respectable until you remember that 0.064% of anything is essentially nothing with aspirations. At that speed, the trip to Alpha Centauri would take approximately 6,800 years, an improvement certainly. Instead of 73,000 years, you're down to a mere 68 centuries. You would arrive right around the time that whatever civilization exists on Earth has probably forgotten you were sent. Historians still argue whether deep future civilizations would even be able to decode the messages we put on our probes. The gold records on the Voyagers, the engraved plaques on the Pioneers, or whether our cultural context would be as opaque to them as Linear A is to us today. Here is a detail that might amuse you in a gently tragic way. The Helios 2 probe, a joint NASA and West German space mission launched in 1976, held the spacecraft's speed record for over 4 decades at about 70 kilometers per second. It was designed to study the Sun, not to leave the solar system, and it eventually lost contact and presumably now orbits the Sun in perpetuity as a silent dead piece of human ambition circling a star that does not notice it. Before Parker Solar Probe eclipsed its record, Helios 2 was the fastest thing we had ever built, and even it would have needed roughly 18,000 years to reach Alpha Centauri. The fastest thing humanity manufactured for 40 consecutive years was a solar weather station, and it still was not fast enough by a factor of several thousand. There is a joke in there somewhere, but it is the kind of joke that makes you exhale through your nose rather than laugh. The fundamental problem is not engineering ambition. The problem is physics, specifically the rocket equation, derived by Konstantin Tsiolkovsky in 1903 and still haunting aerospace engineers like a ghost that refuses to leave the building. The rocket equation dictates that the amount of fuel you need increases exponentially with the speed you want to reach. To go faster, you need more fuel. To carry more fuel, you need even more fuel to carry the fuel. It is a vicious spiral that ends with your spacecraft being 99% fuel tank and 1% everything else, and you still are not going fast enough. Chemical rockets, the kind we have been using since the 1940s, are limited by the energy density of their fuel. You burn hydrogen and oxygen, you get a certain amount of thrust, and there is a hard ceiling on how efficient that process can ever be, no matter how clever the engineering. That ceiling is nowhere near high enough for the stars. You let out a slow breath. The stars above have not moved. They never move, not on human timescales, and the machines we have hurled at them, our fastest and finest, are like paper airplanes thrown into a hurricane. Elegant, earnest, and nowhere near enough. But there is something oddly soothing about that, is there not? The universe is so large and our machines are so small, and yet we keep building them. We keep throwing them upward. We keep tracking their signals for decades, listening for whispers from objects that have passed beyond the reach of our sun's warmth. Voyager 1 is still talking to us faintly, its radio signal so weak by the time it reaches Earth that the power received is roughly 10 to the negative 16 watts, about 20 billion times weaker than the power needed to run a digital wristwatch. And we hear it. We built antennas sensitive enough to hear it. That is not just engineering, that is love, expressed in metal and mathematics, and you can carry that thought with you as the night grows deeper. Let us make this personal. Forget rockets for a moment. Forget engineering. Forget funding cycles and propellant chemistry and the Tsiolkovsky equation. Let us talk about you, your body, your legs, your shoes, the ones by the door, and what it would take for you to walk to Alpha Centauri. The average human walking speed is about 5 kilometers per hour. A pleasant stroll, the kind of pace where you can still hold a conversation, point at interesting birds, and not break a sweat. At 5 kilometers per hour, walking non-stop, no sleep, no meals, no bathroom breaks, no existential crises about why you're walking to another star, you would cover about 120 kilometers per day. To cover 41.34 trillion kilometers at that rate, you would need approximately 344.5 billion days. Divide by 365 and you get roughly 943 million years, nearly a billion years. For context, a billion years ago, the most complex life on Earth was probably single-celled organisms debating whether to develop a nucleus. You would start walking before multicellular life existed and arrive after the sun had noticeably changed its energy output and the continents had rearranged themselves into configurations no geologist alive today could predict. Your shoes would need replacing roughly every 800 kilometers, which means you would go through about 51.7 billion pairs. The entire global shoe industry, running at full capacity, every factory on every continent, could not keep up with a single interstellar pedestrian. Nike's stock would do very well for a while, then everyone at Nike would be dead for 900 million years, and you would still be walking. Fine. Walking is absurd. What about driving? A car on a highway cruises at about 100 kilometers per hour. Same conditions. No stops, no fuel, no mechanical failures, no construction zones on the interstellar highway, just pure continuous forward motion through the void. At 100 kilometers per hour, the trip to Alpha Centauri takes about 47 million years. Better than walking, sure, but still roughly the amount of time that separates us from the extinction of the non-avian dinosaurs, the ones whose absence allowed mammals to flourish and eventually produce a species neurotic enough to calculate how long it would take to drive to another star. You would leave before the Himalayas finished forming and arrive well after they had eroded back to rolling hills. Your car's warranty would have expired so thoroughly that the concept of a warranty, the concept of a car, the concept of a road, and the concept of the company that sold it to you would all have ceased to exist in any recognizable form. What about flying? A commercial Boeing 747 cruises at about 920 kilometers per hour. Roomy seats? Well, not that roomy. Mediocre food. That one crying baby in row 14 who somehow cries for the entire flight even though the flight is 5.1 million years long. At that speed, Alpha Centauri is roughly 5.1 million years away. You would board the plane during the Pliocene epoch, when our ancestors were just beginning to walk upright and were deeply confused about most things. You would land in a future so distant that predicting it is like trying to predict today's geopolitics from the perspective of a 4-foot-tall hominid who has just discovered that rocks can be sharp if you bang them together. The in-flight movie selection would have to be extraordinary. Here is a quirkier comparison that sports fans might appreciate. The fastest human foot speed ever recorded was Usain Bolt during the 2009 World Championships in Berlin, where he hit a peak speed of approximately 44.72 kilometers per hour during the 100-meter final. If Bolt could sustain that speed indefinitely, which he cannot because he is a human being and not a perpetual motion machine, and also he is retired and presumably enjoying himself, the trip would take about 105 million years. He would start running in the Cretaceous period, dodging tyrannosaurs and wondering what that bright streak in the sky was, and arrive in a future where the constellations themselves have visibly shifted and Alpha Centauri is no longer even the nearest star. Even the fastest human who has ever lived, frozen at the absolute peak of his physical perfection, running forever without rest or complaint, cannot beat the distance. The distance does not care how fast you are, it simply does not care. Historians still argue about the earliest long-distance journeys undertaken by humans, the migration out of Africa, the Polynesian voyages across the Pacific, the Aboriginal settlement of Australia tens of thousands of years ago, and in every case those journeys took generations of cumulative effort and courage. The Pacific Islanders who colonised Hawaii sailed roughly 4,000 kilometres of open ocean using only the stars, the behaviour of ocean swells, the flight patterns of birds, and an extraordinary mental map of the sea passed down through oral tradition. That journey took perhaps a few weeks to a month. It was one of the most remarkable feats of navigation in human history, and it deservedly inspires awe to this day. And it covered a distance that is, compared to the trip to Alpha Centauri, roughly equivalent to the distance an ant covers when it twitches one leg. The Polynesians crossed a puddle. We're trying to cross an ocean that stretches to the horizon in every direction and never, ever ends. But here is the funny thing, and I mean funny in that cosmic, absurd, slightly sad way that only the universe can deliver. We keep making these comparisons and they keep failing. Every analogy breaks. Every metaphor collapses under the weight of the actual numbers. You say, it is like driving to Alpha Centauri, and the number of years is so large it becomes noise. You say it is like walking, and the number becomes even larger noise. The human brain was not engineered for this. It was engineered for the savannah, for that tree is about 3 days' walk, and the river is half a morning away. Interstellar distances exist in a category that has no drawer in the filing cabinet of human intuition. You can know the numbers, you can write them down, but you cannot feel them. Not really. Not the way you can feel the distance between your bed and the kitchen at 2 a.m. when you want a glass of water and the floor is cold. And so instead of feeling the distance, you just let it wash over you. You're lying down. The stars are up there, absurdly far away. The nearest one is a 1 billion-year walk, a 47 million-year drive, a 5 million-year flight. And somehow, knowing that, you feel not smaller, but lighter. Because if the universe is that large, and you are that small, then whatever kept you awake tonight, whatever worry, whatever deadline, whatever argument with someone you love, is so microscopically tiny against that backdrop that it barely registers as a quantum fluctuation in the grand scheme. You breathe in, you breathe out. And the distance becomes, paradoxically, a kind of comfort. So what is actually out there, between here and there? You have established that the distance is staggering. You have tried to shrink it, to analogize it, to drive and walk and sprint it into something your brain can hold without flinching. But you have not yet looked at the space itself, the actual physical stuff that fills those 4.37 light years. And the answer, it turns out, is almost nothing, which is somehow the most unsettling answer of all, because human beings can handle danger, can handle obstacles, can even handle hostility, but emptiness, true emptiness, the kind that does not even have the decency to contain dust, is something else entirely. Interstellar space, the vast regions between star systems, is the closest thing to a perfect vacuum that the universe offers outside of certain laboratory experiments. On average, it contains about 1 atom per cubic centimetre. 1. A single, lonely atom, drifting in a volume of space you could fit a sugar cube into. For comparison, the air you're breathing right now contains about 25 quintillion molecules per cubic centimetre. The difference between the air in your lungs and the void between the stars is so extreme that no analogy captures it. If the air in your room were a packed stadium, interstellar space would be one person standing alone in an area the size of several Earths. Most of those lonely atoms are hydrogen, the simplest element, just one proton and one electron drifting through the dark at a few tens of kilometers per second like a tourist who has lost their group. Some are helium. A tiny fraction are heavier elements, carbon, oxygen, iron, cooked up in the cores of long-dead stars and scattered into space by supernovae billions of years ago. This thin scattering of atoms is called the interstellar medium, and astronomers have been studying it for over a century, mapping its density, temperature and composition with radio telescopes, ultraviolet spectrometers, and the occasional spacecraft that actually passes through it and sends back measurements from the other side of the heliosphere. The local neighbourhood of interstellar space, the specific region between us and Alpha Centauri, is particularly sparse, even by interstellar standards. Our solar system sits inside what is known as the local bubble, a region of space roughly 300 light-years across that is even emptier than the already absurd interstellar average. The local bubble was likely carved out by a series of supernova explosions that occurred between 10 and 20 million years ago, which swept the surrounding gas and dust outward like a cosmic snowplow, leaving behind a hot, thin cavity. The density inside the local bubble is roughly 0.05 atoms per cubic centimetre, 20 times less than the already absurdly low average of interstellar space. You are looking at a void within a void, a quiet room inside an already silent house, inside a neighbourhood where no one lives. There is, however, a small, slightly denser patch within the local bubble called the local interstellar cloud, or sometimes the local fluff, a name that sounds like it was invented by a scientist who also knits, and I mean that as a compliment because knitting and astrophysics are both exercises in patient pattern recognition. The local fluff is a warm cloud of partially ionized gas, about 30 light-years across, through which our solar system is currently moving at roughly 26 kilometers per second. Its density is a comparatively luxurious 0.3 atoms per cubic centimetre, and its temperature is roughly 6,000 Kelvin, warm enough to keep the hydrogen partially ionized, but still cold enough by stellar standards to be considered a gentle bath rather than a furnace. Alpha Centauri sits on the edge of the local fluff, or possibly just outside it, depending on whose model you consult and which paper you read last. Historians still argue about the exact boundaries, because mapping interstellar gas clouds at this resolution is like trying to determine the exact edge of fog from inside the fog while the fog is moving, and you're also moving and neither of you has a map. But even the local fluff, dense by local standards, is effectively nothing by human standards. You could fly through it at any speed and never notice a single particle hitting your hull. A spacecraft traversing interstellar space would encounter so few atoms that the main threat is not collision, but the sheer, crushing, existential weight of isolation. The danger of the void is not what is in it. The danger is what is not in it. No fuel depots, no raw materials, no way to break or resupply. You're a sealed tin can moving through emptiness so profound that if you ran out of power, you would drift, cold and silent, forever, and nothing would ever find you. Not because space is hostile, space is indifferent, which is worse. A hostile environment is at least paying attention to you. There is one more thing out there though, and it is worth mentioning as you let your muscles relax and your thoughts soften. Cosmic rays, high energy particles, mostly protons but also heavier atomic nuclei, that zip through interstellar space at nearly the speed of light. Some originate from the Sun, some from distant supernovae, some from the supermassive black holes at the centres of other galaxies firing particle jets across millions of light years. Inside the solar system, Earth's magnetic field and atmosphere shield you from most of them. You're bathed in cosmic radiation every day, but the dose is manageable. In interstellar space, however, there is no shield. A human body exposed to the full flux of galactic cosmic rays for years on end would accumulate radiation damage far beyond safe limits. Your DNA would be chipped away at, error by error, mutation by mutation, like a book being slowly erased one letter at a time until the sentences no longer make sense. This is one of the many unsolved problems that any crewed interstellar mission would need to address, and it is one of the reasons that the emptiness between here and Alpha Centauri is not just boring, but actively, silently dangerous. And yet even the danger is quiet. There is no dramatic moment, no explosion, no alarm bell, just a slow, invisible rain of particles ticking against the hull of a ship that no one has built yet, in a silence so deep that the word silence does not do it justice. You think about that as the night wraps around you. The void is vast and empty and patient. It has been waiting for billions of years. It will wait for billions more. And if you or your descendants ever cross it, the void will not welcome you or resist you. It will simply be there, as it always has been, indifferent and immense and profoundly, achingly still. So there is a planet. Of course there is a planet, because the universe has a sense of dramatic timing that would put any screenwriter to shame, and it placed a rocky, possibly habitable world right next door, just close enough to tease us and just far enough to be completely out of reach. In August 2016, a team of astronomers led by Guilherme Anglada Escude at Queen Mary University of London announced the discovery of a planet orbiting Proxima Centauri. They named it Proxima Centauri b, because astronomers name things the way accountants name spreadsheet tabs, with all the poetic flair of a filing system, and it set the entire scientific world buzzing with a particular kind of excitement that only comes from finding something extraordinary in your own backyard. Not because exoplanets were new. By 2016, NASA's Kepler Space Telescope had already discovered thousands of them, orbiting stars across the Milky Way. But because this one was different, this one was next door. This one was orbiting the nearest star to our Sun, and it was sitting in the habitable zone. Proxima Centauri b orbits its star at a distance of about 7.5 million kilometres, much closer than Earth orbits the Sun. But remember, Proxima is a red dwarf, far dimmer and cooler than our star, so the habitable zone, the region where temperatures are right for liquid water, is correspondingly closer in. The planet sits right in that zone, like Goldilocks sitting in the smallest chair. It completes one orbit every 11.2 Earth days, which means a year on Proxima b lasts less than 2 weeks. Your birthday would come around roughly 33 times per Earth year. You would run out of cake before March, and your friends would stop returning your party invitations by April. The planet is estimated to be at least 1.17 times the mass of Earth, making it a rocky world, not a bloated gas giant like Jupiter or Saturn. Its exact size is unknown because the discovery was made using the radial velocity method, detecting the tiny wobble the planet's gravity induces in its star as it orbits, which gives you mass but not diameter. It could be slightly larger than Earth, or about the same size with a denser composition, packed with iron and silicates. Either way, it is the kind of world where, if you squint at the data and allow yourself a generous amount of optimism and maybe a glass of wine, you can imagine standing on solid ground under an alien sky, looking up at a dim red sun that takes up more of the sky than ours does, and feeling something beneath your feet that is undeniably, recognizably ground. But, and this is a significant but, the kind of but that scientists deliver with a slight wince and a careful clearing of the throat, Proxima Centauri is not a kind host star. Remember those flares we talked about in Section 2? Proxima b orbits so close to its star that it receives roughly 400 times more X-ray radiation than Earth does from the Sun. A super flare like the one detected in 2016 would strip the ozone layer of an Earth-like atmosphere in a geological heartbeat and bombard the surface with enough ultraviolet radiation to sterilize the top layers of any exposed ocean. Historians still argue whether M-dwarf planets like Proxima b can retain atmospheres at all over billions of years, given the relentless bombardment. Some models suggest a thick atmosphere could survive if it were continuously replenished by volcanic outgassing from the planet's interior. Others suggest the atmosphere would be stripped completely within a few 100 million years, leaving a bare, airless rock baking in hard radiation, like a potato forgotten in a very angry oven. There is also the issue of tidal locking. Because Proxima b orbits so close to its star, it is very likely tidally locked, one side permanently facing the star, the other in eternal night, with a narrow twilight strip running between them. The day side could be scorching, the night side frozen solid. But that twilight zone, the terminator, as planetary scientists call it, might be just right. Some climate models suggest that with the right atmospheric circulation, winds could distribute heat from the day side to the night side efficiently enough to allow liquid water in the terminator region. It would be a strange world, a world with a permanent sunset painted across the sky in every direction you look, a world where you would always know which direction warm was and which direction cold was, and you would live your life in the narrow ribbon between the two. And here is the quirky part, the detail that makes you smile in the dark and pull the covers a little tighter. In 2020, astronomers detected an unusual radio signal from the direction of Proxima Centauri using the park's radio telescope in Australia, as part of the Breakthrough Listen project. It was a narrow band signal at 982 MHz that appeared to shift in frequency in a way consistent with a transmitter on a rotating planetary surface. For a brief, thrilling, slightly terrifying moment, the world collectively held its breath. Was it a signal from Proxima b? Was someone, something, saying hello from across 4.2 light-years of void? The answer, after months of painstaking analysis published in 2021, was almost certainly no. The signal, designated BLC1, was most likely terrestrial interference, a human-made radio signal from somewhere on Earth that had been reflected or refracted in a way that mimicked an extraterrestrial source. But for those months between detection and explanation, the possibility hung in the air like a held note in a song that everyone was afraid to finish. It reminded us why we look. It reminded us why we listen. It reminded us why the distance, however terrifying, does not stop us from pressing our ears to the cosmos and hoping for a whisper. You lie there and you imagine it. A rocky world, slightly heavier than Earth, orbiting a star you can barely see from your backyard. A star so faint that the ancient Greeks never even noticed it. a world where the sun never sets on one side and never rises on the other, a world that might have water, might have an atmosphere, might even have something looking back at us across the light years and wondering the same things we wonder about them. Or it might be a lifeless, irradiated rock, beautiful only in the way that desolate places are beautiful, for their silence, their emptiness, their complete indifference to the hopes we project onto them from 4.2 light years away. Either way, it is there, it is real, it is confirmed, and the tension between the tantalizing possibility of what might be there and the crushing reality of how far away it sits is the thread that runs through everything tonight. You tug on it gently, not to unravel it, but just to feel its weight. Before you even dream of reaching Alpha Centauri, you have to get out of your own backyard. And your backyard, it turns out, is bigger than you ever imagined. Much bigger. Terrifyingly bigger, because surrounding our solar system, like a vast invisible fence made of ice and rock and ancient debris left over from the formation of the planets, is the Oort cloud. And the Oort cloud does not care about your travel plans. The Oort cloud is named after Jan Hendrik Oort, a Dutch astronomer who proposed its existence in 1950 to solve a nagging puzzle. Where do long-period comets come from? Some comets, like Halley's, have short orbits traceable to the Kuiper belt beyond Neptune, but others take thousands or millions of years to complete one trip around the Sun, arriving from every direction. They have to come from somewhere spherical, somewhere enormous, somewhere very far away. That somewhere, Oort reasoned, is a colossal spherical shell of icy bodies surrounding the solar system at distances between roughly 2,000 and 100,000 astronomical units from the Sun. Let those numbers breathe for a moment. 100,000 astronomical units. One astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. So the outer edge of the Oort cloud sits roughly 15 trillion kilometers from the Sun. That is about 1.58 light years, and Alpha Centauri is 4.37 light years away. Which means the Oort cloud extends roughly a third of the way to the nearest star. You have not even left the solar system's extended property line, its outermost suburban sprawl, and you have already covered a terrifying fraction of the journey. Or, looked at another way, you have to cross the equivalent of about 3 Oort clouds stacked end to end, plus some extra void for good measure, to reach Alpha Centauri. Your own cosmic backyard fence stretches so far that merely jumping it is itself an interstellar-scale challenge that would take our fastest spacecraft tens of thousands of years. Nobody has ever seen the Oort cloud directly. Not a single object in it has been imaged or visited. It is too far, too dark, and its constituent objects are too small and too scattered to reflect enough sunlight to be detected with current telescopes. Its existence is inferred entirely from the behavior of the comets it periodically sends our way, like a neighbor you've never seen but whose existence you deduce from the packages that occasionally land on your doorstep. This is one of those beautiful features of science. You can deduce the existence of something you cannot see by watching what it does, like knowing someone is in the next room because you can hear them humming softly. Historians still argue about the exact structure of the Oort cloud, whether it is truly spherical or slightly flattened along the plane of the galaxy, whether it has a sharp outer boundary or fades gradually into interstellar space like the edge of a fog bank, whether it contains billions or trillions of objects. The estimates range wildly, from a few 100 billion to several trillion icy bodies larger than 1 kilometer in diameter, with a total mass of perhaps 5 to 100 Earth masses. The uncertainty is enormous, and the truth is simply that we do not know, because we cannot look. Not yet. Here is a quirky detail that might lodge itself in your drowsy mind like a burr in a sock. The objects in the Oort cloud are so far from the sun that its gravitational grip on them is tenuous, like holding a dog on a leash made of thread. A passing star, or even the slow tidal forces of the Milky Way galaxy itself, as the sun orbits the galactic center, can perturb their orbits, nudging them inward toward the sun or outward into interstellar space. This is how long-period comets are born. A gentle gravitational nudge, maybe from a star passing within a light year or two, sends an icy body on a million-year fall toward the inner solar system, where it heats up, develops a spectacular tail of gas and dust, and briefly becomes the most photogenic thing in the sky, before swinging back into the dark. In 1999, astronomer Joan Garcia Sanchez used data from the Hipparcos satellite to identify stars that have passed close to the Oort cloud in the past and will do so in the future. She found that roughly 12 stars pass within 2 light-years of the Sun every million years, close enough to rattle the Oort cloud like a fist knocking on a door and send fresh volleys of comets cascading inward. The universe plays a slow, gentle game of billiards with our solar system, and the Oort cloud is the collection of balls waiting patiently to be scattered across the table. And this matters for our journey to Alpha Centauri because any spacecraft heading that way will have to pass through the Oort cloud, slowly at first because the inner reaches are relatively close, but then for an agonizingly long stretch of time because the cloud extends so mind-numbingly far. If you're on a spacecraft travelling at 10% of the speed of light, which is already a speed we have absolutely no idea how to achieve, the Oort cloud alone would take roughly 15 years to cross. At Voyager's speed, it would take about 30,000 years. 30,000 years inside a shell of invisible ice and rock with no landmarks, no signposts, no way to know how far you've come or how far you have left to go except by checking the math. The interstellar void beyond the Oort cloud is almost a relief by comparison, because at least the void is honest about its emptiness. The Oort cloud pretends to be part of home while being incomprehensibly far from everything you have ever known. You think about that as your breathing softens. You think about the last object in the Oort cloud that your hypothetical spacecraft would pass, the final icy sentinel of the solar system, a chunk of frozen water and methane and ammonia that has been orbiting the sun for 4.5 billion years, so far out that the sun is just another bright star in its sky, indistinguishable from the millions of others. You wave goodbye to it mentally and you keep going. Beyond the fence, beyond the yard, into the space between the houses, where the streetlights end and the dark begins in earnest. Your breathing is slower now. The night has settled around you like a blanket, and the Oort cloud, for all its strangeness, has a kind of quiet grandeur to it. 1 trillion comets, asleep in the dark, waiting for a nudge. You know the feeling. You're waiting for a nudge too. The nudge of sleep, the soft push into dreams. But not yet. There is more distance to cover, and the journey is far from over. So how do you actually get there? Not in theory, not in a thought experiment involving shoes and highways, but in practice. What technology exists right now, today, bolted to actual spacecraft and tested in the actual vacuum of actual space, that could theoretically propel something across 4.37 light-years? The answer is humbling, but it is not nothing. There are engines, real engines. They have been built and tested and flown. They are just very, very slow. Magnificently, elegantly, almost poetically slow. Ion drives. You may have heard the term in science fiction, where they are depicted as glowing blue exhausts on sleek starships. The reality is less photogenic but more elegant. An ion drive works by ionizing a propellant, usually xenon gas, and accelerating the resulting ions through an electric field to produce thrust. The thrust is tiny, absurdly tiny. The ion drive on NASA's Dawn spacecraft, which orbited the asteroid Vesta and the dwarf planet Ceres, produced about 90 millinewtons of force. That is roughly the weight of a single sheet of paper resting on your palm. You could hold your hand out flat, place one piece of printer paper on it, and say, "This is how hard Dawn's engine pushes," and you would be exactly right. But here is the trick. Ion drives are extraordinarily efficient. They use propellant so sparingly that they can run for years, even decades, producing that tiny push continuously. And in the frictionless vacuum of space, tiny pushes add up. Dawn's ion drive, running continuously, could accelerate by about 10 kilometers per second over a year. It is the tortoise in the fable, except the hare is a chemical rocket that burns bright and fast and then coasts forever, while the ion drive just keeps going, patiently accumulating speed day after day. The most advanced ion drive currently in development is NASA's NEXT-C, the NASA Evolutionary Xenon Thruster, commercial variant, which produces about 236 millinewtons, roughly 2.5 times Dawn's engine. There are also Hall-effect thrusters, which are a related but mechanically distinct technology used by SpaceX's Starlink satellites to maintain their orbits. These are even lower thrust, but extraordinarily efficient at their operational scale. For interstellar travel, you would need something much larger, an ion drive scaled up by orders of magnitude, powered not by solar panels, which become useless far from the sun, but by a nuclear reactor capable of providing electricity for decades or centuries of continuous operation. At the speeds achievable by current ion drive technology, even optimistic estimates place the travel time to Alpha Centauri at around 50,000 to 100,000 years. That is a long commute. That is so long that the concept of commute loses all recognizable meaning, and you're better off thinking of it as a geological process, something measured on the same timescale as the formation of mountain ranges and the drift of continents. But the technology is real. It exists. People have built it, tested it, flown it to other worlds, and it worked. It is slow, but it is a start, and sometimes a start is all you need to keep the dream alive. Solar sails are the other contender in the slow but plausible category. The idea is elegant. You unfurl a large, thin, reflective surface and let the pressure of sunlight push you forward, the same way a sailboat catches wind. Except instead of wind, it is photons, and instead of an ocean, it is the void of space. Photons have no mass, but they carry momentum, and when they bounce off a reflective surface, they transfer that momentum as a tiny push. A solar sail the size of a football field would experience a force of about 9 newtons, roughly the weight of a 1-litre bottle of water. Not much, but in the vacuum of space, not much is enough if you are patient. The first solar sail spacecraft actually flown was Icaros, launched by the Japan Aerospace Exploration Agency in 2010. It was a 14-metre square sail, made of a polyamide film thinner than a human hair, that successfully demonstrated solar sail propulsion in interplanetary space. A historical first that received far less media attention than it deserved, probably because it was not as telegenic as a rover driving around Mars or a rocket landing itself on a barge. The Planetary Society followed up with LightSail 2 in 2019, a CubeSat-sized solar sail that successfully raised its orbit using nothing but reflected sunlight. Historians still argue about whether Johannes Kepler, who observed that comet tails always point away from the sun, and speculated about what he called solar wind pushing them, deserves credit as the first person to conceive of solar sailing, back in the early 1600s. If so, it took roughly 400 years to go from concept to flight test, which is either depressingly slow or inspiringly persistent, depending on your mood and your relationship with delayed gratification. For interstellar travel, a solar sail has one major advantage over every other propulsion system: it needs no fuel. As long as there is light, there is thrust. No tanks, no combustion, no supply chain. But there is a catch. The farther you get from the sun, the weaker the light, and the weaker the thrust. By the time you're at Jupiter's orbit, sunlight is only about 4% as intense as at Earth's. By Saturn, it is roughly 1%. A pure solar sail becomes increasingly useless the farther it gets from its parent star, like a sailboat drifting into a region where the wind simply stops. To get serious interstellar speeds, you would need to start very close to the sun, where the light is intense, and use that initial blast of photon pressure to sling yourself outward as fast as possible. Some proposals suggest diving within a few solar radii of the sun, close enough to feel the star's thermonuclear breath on the sail's surface, and then riding that intense light pressure outward like a surfer catching the wave of a lifetime. The theoretical speeds are impressive, perhaps 0.1% of the speed of light, or even higher with exotic ultra-reflective sail materials. But even at that speed, Alpha Centauri is still over 4,000 years away. You let the image linger, a vast shimmering sail, thinner than a human hair, unfurling in the light of the sun, silent, patient, accelerating by imperceptible increments, year after year, carrying no fuel, producing no exhaust, just riding the light toward a destination it will not reach for millennia. There is something almost spiritual about it, a technology that runs on starlight and patience, two things the universe has in infinite supply, and as your own patience with wakefulness begins to thin, that image feels exactly right, slow, gentle, inevitable. Now here is where the dreamers get bold, because while ion drives and solar sails are real but slow, there is a project, an actual, funded, serious, billionaire-backed project that aims to send something to Alpha Centauri within a single human generation. It is called Breakthrough Starshot, and it is either the most audacious engineering proposal in human history or the most expensive thought experiment ever funded by a check that did not bounce, possibly both simultaneously. Breakthrough Starshot was announced in April 2016 by Yuri Milner, a Russian-Israeli billionaire and science philanthropist, with Stephen Hawking and Mark Zuckerberg sitting on the board of directors. The idea is disarmingly simple in concept and terrifyingly complex in execution. Build a ground-based laser array somewhere dry and high, point it at a tiny spacecraft equipped with a light sail, and blast it with enough photons to accelerate it to 20% of the speed of light. At that speed, roughly 60,000 kilometers per second, which is so fast that the number almost stops meaning anything, the trip to Alpha Centauri would take about 20 years. Add another 4.37 years for the data to travel back to Earth at the speed of light, and you could, in theory, get your first close-up images of the Alpha Centauri system within about 25 years of launch. A single human lifetime. Your lifetime, potentially, if the engineering gods are feeling generous and the funding holds out. The spacecraft, or Starship as the team calls it, because even interstellar exploration needs branding, would be about the size of a postage stamp and weigh roughly 1 gram. 1 gram, the weight of a paperclip. It would carry a camera, a navigation system, a communication laser, and a power supply, all miniaturized onto a single silicon wafer using techniques borrowed from the semiconductor industry. The light sail would be about 4 meters across, thinner than a human cell, and made of some material that does not yet exist, something that can reflect a very high fraction of the laser energy without melting, absorbing, or deforming under the most intense directed energy beam ever conceived. The laser array itself, which is the really wild part that keeps engineers awake at night with a mixture of excitement and dread, would need to produce about 100 gigawatts of power, focused into a beam tight enough to illuminate a 4-meter sail at a distance of millions of kilometers. For reference, 100 gigawatts is roughly the total electrical generating capacity of a medium-sized country, something like France or the United Kingdom. You would need to fire this beam for about 10 minutes per launch, during which time the Starship would accelerate from 0 to 60 million meters per second. The G-forces during that acceleration would be around 60,000 times Earth gravity. The chip would have to survive being compressed with the force of a small building sitting on top of it for 10 straight minutes. Your phone screen cracks when you drop it from waist height. This chip would need to survive forces that would crush a submarine. Historians still argue about whether Breakthrough Starshot represents a genuine, achievable engineering roadmap or an inspirational target, a North Star, if you will, that is meant to drive research in the right general direction, even if the specific mission as described never actually flies. The challenges are extraordinary and interconnected. The laser array would be the most powerful directed energy system ever built by a factor of thousands, and aiming it precisely enough to hit a 4-meter sail at rapidly increasing distances would require tracking accuracy that makes our best current telescope pointing systems look like aiming a garden hose. The sail material, ultra-lightweight, ultra-reflective, ultra-heat-resistant, ultra-everything, does not currently exist and would need to be invented essentially from scratch. The communication system would need to beam data back across 4.37 light-years, using a laser powered by the minuscule energy budget of a 1-gram chip, and the receiving telescope on Earth would need to be sensitive enough to detect that whisper against the background noise of the cosmos. Each of these challenges is, on its own, at the bleeding edge of current technology. Solving all of them simultaneously, reliably, and cheaply enough to launch not one, but a fleet of thousands of starships, because many will be lost to interstellar dust impacts and other hazards, is a problem that would keep the world's best engineers employed for decades. But here is the thing, and this is the part that makes Breakthrough Starshot more than a billionaire's expensive daydream. None of the individual technologies violate the laws of physics. Every single component is theoretically possible. The laser power is achievable with current technology, just not at the required scale. The sail materials are within the range of what materials scientists believe they can develop within the next few decades. The miniaturization of sensors and processors continues at a pace that would make a 1-gram spacecraft plausible within a generation. The project is not asking for new physics, it is asking for new engineering, and engineering, unlike physics, is negotiable. You can throw money and talent and time at engineering problems, and eventually, stubbornly, one iteration at a time, solve them. Physics problems are take it or leave it. Engineering problems are how much do you want it? Here is a quirky detail that often gets lost in the grand vision and the big numbers. If Breakthrough Starshot works, if a fleet of 1-gram chips actually reaches Alpha Centauri at 20% of the speed of light, there is no way to slow them down, no braking system, no reverse thrust. They would blow through the entire Alpha Centauri system at 60,000 kilometers per second, getting perhaps a few hours of close observation before vanishing into the interstellar void on the far side. No orbiting, no landing, no second look. You get one shot, a flyby so fast that the triple star system and all its planets would pass in and out of camera range in a matter of hours. The cameras would need to capture everything in that brief window. Images of Proxima Centauri b, spectral data on the atmospheres of any planets, measurements of the stars and their interactions. And then the chip sails on, into the dark forever, carrying those images in its memory like a dream it cannot share with anyone. There is something deeply poignant about that. A tiny piece of human ingenuity, smaller than a cracker, hurtling through the cosmos at 1/5 the speed of light, having glimpsed another star system for a fleeting glorious moment, and then spending eternity drifting in the void with those images locked inside it. Like a message in a bottle thrown into an ocean that has no other shore. You think about that as you settle deeper into the dark, and it stays with you. Before lasers and nanochips and silicon wafers the size of postage stamps, there was another plan. A louder plan. A plan that involved, and I want you to hear this clearly because it sounds like a joke but is entirely, completely, historically real, surfing nuclear explosions to the stars. Project Orion was conceived in 1958 by physicist Ted Taylor and mathematician Freeman Dyson at General Atomics in San Diego. The concept was straightforward in the way only Cold War-era thinking could manage. Build a massive spacecraft with a thick pusher plate at the rear and propel it by ejecting nuclear bombs out the back and detonating them in rapid succession. Each explosion would slam a pulse of plasma into the pusher plate, shoving the ship forward. Do this a few thousand times, and you have a spacecraft accelerating at a rate that makes chemical rockets look like a child blowing on a paper boat. The numbers were staggering. The smallest proposed Orion design was a few hundred tons, using small tactical nuclear devices. The largest, the Super Orion, would have been the size of a city block, 8 million tons, propelled by hydrogen bombs detonated roughly 1 per second, capable of reaching 3 to 5% of the speed of light. At 5% of light speed, roughly 15,000 kilometers per second, the trip to Alpha Centauri would take about 85 years, still longer than a single human lifetime, but within the range where you might conceivably leave Earth as a young adult and arrive as a very old person, assuming you survived both the journey and the not insignificant amount of radiation involved in riding nuclear explosions for nearly a century. Project Orion was not just a thought experiment. General Atomics actually built and tested a 1-meter prototype called Hot Rod or Put-Put. Propelled by conventional chemical explosives at Point Loma, California in 1959, the little model flew beautifully, rising smoothly on carefully timed detonations, proving that pulse propulsion actually worked. The team was elated. They had designs for missions to Mars, Saturn, and beyond. Freeman Dyson later described Orion as the first interstellar transportation system that we could build with known technology. Then the Partial Nuclear Test Ban Treaty of 1963 happened, and everything changed. The treaty prohibited nuclear detonations in the atmosphere, in outer space, and underwater. And while Project Orion was not specifically mentioned in the text, it was, after all, a somewhat niche concern compared to the broader goal of preventing nuclear war. it effectively killed the project dead. You cannot test a nuclear pulse spacecraft without detonating nuclear devices in space, and the treaty said you could not detonate nuclear devices in space. The funding dried up, the team disbanded, and one of the most ambitious propulsion concepts in human history was shelved, not because the physics was wrong or the engineering was impossible, but because the politics were, quite understandably, complicated. The world had decided reasonably that setting off nuclear bombs was something to be done less of, not more of, even if the goal was reaching the stars. Historians still argue about whether Orion could have actually worked at interstellar scales. The engineering challenges beyond the basic concept were formidable. How do you build a pusher plate that can survive thousands of consecutive nuclear detonations without eroding into uselessness? How do you store and deploy thousands of nuclear devices reliably over decades of flight? How do you shield the crew from cumulative radiation exposure? Each question had proposed answers in the original studies, but none of those answers were tested beyond the conceptual stage. Some physicists believe Orion was genuinely feasible with 1960s technology, and that the test ban treaty was the only thing standing between humanity and an interstellar-capable spacecraft. Others argue that the challenges would have proven insurmountable at scale, that the optimism was a product of the era's particular blend of can-do attitude and nuclear enthusiasm, and that scaling up from a 1-meter model to a city block-sized starship riding hydrogen bombs is not a straightforward engineering exercise. Here is a quirky detail that I genuinely adore, and that tells you everything about the mindset of the people who work on interstellar propulsion. Freeman Dyson, who worked on the project and remained its most passionate public advocate until his death in February 2020, at the age of 96, once calculated that the radioactive fallout from a full-scale Orion launch from the surface of the Earth would statistically cause about 1 additional cancer death globally, spread across the entire human population. He considered this an acceptable trade-off for opening the solar system and eventually the stars to human exploration. The general public and the United States government did not share this particular cost-benefit analysis, which is probably reasonable in the grand scheme of things, but Dyson's willingness to do the calculation, present it with a straight face, and stand by it for 60 years tells you everything you need to know about the kind of human being who dedicates their life to getting us off this rock. There were intellectual successors to Orion, each one slightly more refined and slightly less likely to cause international incidents. Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, proposed an unmanned probe propelled by nuclear fusion, not fission bombs, but controlled thermonuclear reactions using tiny pellets of deuterium and helium-3 ignited by concentrated electron beams. Daedalus would have been a 54,000-ton 2-stage behemoth, unmanned and fully autonomous, capable of reaching about 12% of the speed of light and arriving at Barnard's star, 6 light-years away, in about 50 years. Project Longshot, a study conducted by the US Naval Academy in the late 1980s, proposed a similar fusion-powered probe specifically targeted at Alpha Centauri, with an estimated travel time of about 100 years. Neither project was ever built. They exist only as reports, as calculations, as dreams rendered in engineering notation and filed in university libraries. But they proved that serious, rigorous, peer-reviewed analysis could produce plausible interstellar mission designs, and that nuclear propulsion, in one form or another, remained the most credible known path to the stars. You lie there and you picture it. A spacecraft the size of a skyscraper riding a trail of nuclear fire through the void, each explosion a brief silent flash in the eternal dark. Silent because there is no air to carry sound, no atmosphere to shake, just light and plasma and momentum transferred through a steel plate the size of a parking lot. It is absurd. It is magnificent. It is the kind of idea that could only come from a species that simultaneously splits atoms and writes lullabies, that builds weapons capable of ending civilization and then turns around and asks, "But could we use these to visit the neighbours?" Nuclear bombs are dramatic. Fusion is elegant. But if you really want to dream, if you want to imagine the engine that could actually make interstellar travel feel like travel, rather than a generational death march through the void, you need to talk about antimatter. And antimatter is the stuff of dreams in more ways than one, because it barely exists in any usable quantity and costs more per gram than anything else in the known universe, including your most expensive habits. Antimatter is exactly what it sounds like. Matter, but opposite. Every particle has an antiparticle with the same mass but opposite charge. Electron meets positron. Proton meets antiproton. When they collide, they annihilate each other completely, converting 100% of their combined mass into pure energy. All of it. E equals mc squared, the full equation, Einstein's most famous insight, realized perfectly and without waste. By comparison, nuclear fission, the process that powers atomic bombs and nuclear reactors, converts less than 1% of mass into energy. Nuclear fusion does slightly better, managing about 0.7%. Chemical combustion, the process that powers your car engine and got us to the moon, converts such a vanishingly small fraction of mass into energy that it barely registers on the scale at all. Antimatter annihilation is, by any measure, the most efficient energy conversion process permitted by the laws of physics. It is the universe's perfect fuel. 1 gram of antimatter annihilated with 1 gram of ordinary matter, 2 grams total, the weight of a couple of paper clips, would release roughly 180 terajoules of energy. That is approximately 43 kilotons of TNT, roughly 3 times the energy of the bomb dropped on Hiroshima. From 2 grams of stuff you could hold between your fingertips, a spacecraft carrying a few kilograms of antimatter could, in theory, accelerate to a significant fraction of the speed of light. Some designs in the published literature suggest that an antimatter-powered ship could reach 40 to 70% of light speed, reducing the Alpha Centauri trip to a mere 6 to 11 years. Not centuries, not millennia, years. The kind of time frame where you could leave Earth, watch some movies, do a workout routine, read the complete works of Tolstoy twice, arrive at another star system, and still remember what your apartment smelled like. The problem, and you knew there was going to be a problem because the universe is nothing if not consistent in its refusal to make things easy, is making the stuff. Antimatter does not just sit around in convenient deposits waiting to be scooped up like coal or uranium. In the natural universe, it is produced in vanishingly small quantities by cosmic ray impacts and certain kinds of radioactive decay. To get useful amounts, you have to manufacture it, and currently the only way to do that is in particle accelerators like CERN's facility near Geneva, Switzerland, where protons are accelerated to near light speed and smashed into metal targets at enormous energies, occasionally producing antiproton-proton pairs amid a shower of other debris. The production rate is spectacularly, almost comically low. CERN produces roughly 10 to 15 nanograms of antiprotons per year. At that rate, it would take about 100 billion years to produce 1 gram of antimatter, roughly 7 times longer than the current age of the universe. And the cost estimated from the energy and infrastructure required, works out to approximately $62.5 trillion per gram. That is more than the GDP of the United States, for a quantity of fuel you could not see without a microscope. Historians still argue whether antimatter propulsion should be classified as theoretically possible but impractical, or practically impossible but theoretically beautiful, because the line between those two categories is blurrier than most people assume and shifts with every generation of technology. In the 1950s, going to the moon was practically impossible. The technology did not exist. The cost was astronomical in both senses of the word. The engineering challenges were unprecedented. 20 years later, people were hitting golf balls on the lunar surface. Technology has a persistent, stubborn way of making the impossible merely expensive and the expensive merely routine, given enough time and motivation. The question is whether antimatter production can undergo a similar revolution. Some researchers have proposed using focused laser arrays to produce antimatter more efficiently through pair production. Others have suggested harvesting naturally occurring antimatter from the Van Allen radiation belts around Earth, where positrons are known to be trapped in small but detectable quantities by the planet's magnetic field. These ideas are speculative, sitting comfortably in the territory of interesting PhD thesis rather than funded engineering project. But they are not crazy. They are the kind of speculative that attracts serious researchers and generates real papers in real journals. There's also fusion to consider, not the bomb-powered fusion of Project Daedalus, but controlled, sustained fusion, the kind that has been perpetually 30 years away since the 1950s in what is perhaps the longest-running joke in all of physics. If humanity ever cracks fusion power, and recent advances in tokamak design, laser inertial confinement at the National Ignition Facility, and the gradual progress at the massive international ITER facility in southern France suggest we might, eventually, possibly, then fusion-powered spacecraft become a real engineering possibility. A fusion drive using deuterium-helium-3 reactions could theoretically achieve exhaust velocities of several % of the speed of light, enabling travel times to Alpha Centauri of perhaps 50 to 100 years. Not as fast as antimatter, but enormously faster than anything we have today, and using fuel that actually exists in meaningful quantities and does not cost more than the GDP of a superpower per gram. Here is a detail that sits right in the overlap between quirky and heartbreaking, and that captures something essential about where we are as a species. The total amount of antimatter ever produced by humanity, in all the particle accelerators in all the countries in the world combined, since the first antiproton was created at the Bevatron in Berkeley, California, in 1955, would not be enough to boil a cup of tea, not power a city, not launch a spacecraft, not even warm up a mug of Earl Grey to a drinkable temperature. We have been manufacturing the most energy-dense substance in the known universe for 70 years, and our entire accumulated stockpile would barely register on a kitchen thermometer. And yet, we keep making it. We keep studying it. We keep writing papers about antimatter rockets and antimatter drives and antimatter storage, because the physics is too beautiful to abandon, and the dream is too compelling to shelve. It is the ultimate expression of human optimism. We cannot currently make enough of this substance to heat water, but we are already designing starships that run on it. The cookie jar is on the top shelf. Our arms are too short, and somewhere in a lab, a physicist is patiently building a very long pair of stilts. There is another way to cross 4.37 light years, and it does not require faster engines or exotic fuels or laser arrays the size of small countries. It requires something much harder to engineer than any of those things. Patience. Generational patience. The kind of patience that says, I will board this ship knowing I will never arrive, but my great-great-great-great-grandchildren will, and that is enough. Welcome to the concept of the generation ship, which is simultaneously the most practical and the most psychologically terrifying approach to interstellar travel that anyone has ever seriously proposed. A generation ship is exactly what it sounds like, a self-contained habitat, large enough to sustain a human population for centuries or millennia, launched on a slow trajectory toward another star. The people who board the ship at departure know, with full awareness and clear eyes, that they will never see the destination. Their children will not see it. Their grandchildren will not see it. Depending on the speed, their great-great-great-grandchildren might not see it either. The arrival is a promise made to descendants who do not yet exist, a gift wrapped in recycled steel and oxygen and water, delivered across centuries to a generation that will inherit a mission they never chose and a destination they know only from archives. The idea has deep roots. Konstantin Tsiolkovsky wrote about multi-generational space arcs in the early 1900s. Robert Goddard speculated about interstellar migration, but the concept was most rigorously explored in the 1950s and 1960s when engineers ran the numbers. The answers were daunting. You need a ship large enough to maintain a closed-loop ecosystem, air, water, food, waste recycling, for thousands of people over centuries. You need genetic diversity to prevent inbreeding, which requires a minimum founding population of several hundred to several thousand. You need redundancy in every critical system, because there is no resupply and no repair dock. And you need a social structure that can maintain purpose over centuries, which is a challenge that makes the engineering look straightforward. Think about the longest-lived human institutions. The Catholic Church is roughly 2,000 years old. A few universities approach a millennium. Most governments and corporations last a few centuries before collapsing or transforming beyond recognition. A generation ship at 1% of light speed would take about 440 years. At 0.1%, closer to what we could realistically achieve, it would take 4,400 years. Can any human social structure survive 4,400 years? Historians still argue whether the longevity of ancient institutions is evidence that humans can sustain long-term projects, or evidence that they transform so profoundly that the end result bears no resemblance to the original intent. The psychological challenges are equally formidable. Imagine being born on a generation ship. You have never seen a sky, never felt wind, never stood under a sun. Your world is corridors and hydroponics bays and recycled air. Everything you know about your destination comes from records made by ancestors you never met. Your entire existence is defined by a journey you did not choose toward a place you will never reach, because you are a transit generation, born to maintain the ship and produce the next crew. Your role is maintenance. Your reward is the knowledge that the mission continues. Whether that is enough to sustain a human soul for an entire lifetime, no one confidently knows. There's a famous thought experiment in the generation ship literature called The Revolt of the Middle Generations. The first generation, the ones who chose to board, are motivated by the grandeur of the mission and the excitement of departure. The last generation, the ones who arrive, are rewarded by the fulfillment of the mission and the thrill of a new world. But the generations in between, the ones who live and die entirely in transit, who never see departure or arrival, have neither the motivation of choice nor the reward of completion. They are the filling in a multi-generational sandwich, and the fear is that they would eventually reject the mission, lose interest in the destination, forget why the ship is moving, and either settle into a static, insular culture that treats the ship as the entire universe, or actively rebel against a purpose imposed on them by dead ancestors whose decisions they never consented to. Science fiction has explored this scenario with vivid imagination. Novels like Robert Heinlein's Orphans of the Sky and Kim Stanley Robinson's Aurora paint unsettling pictures of generation ships where the original mission has been lost, corrupted, or violently abandoned by people who never asked to be born in a metal tube between the stars. Here is a quirky detail that makes the generation ship concept feel simultaneously grand and deeply, touchingly human. In 2013, a non-profit organisation called Icarus Interstellar conducted a comprehensive study on the psychological and sociological requirements for a viable generation ship. Among their many recommendations, one stood out. The ship should have windows. Not for any practical navigational purpose, there is essentially nothing to see in interstellar space, just blackness punctuated by unmoving stars, but for psychological health. Humans, the study argued, need to feel connected to the outside, even if the outside is a void. They recommended the ship simulate day and night cycles with variable lighting, simulate seasonal changes in temperature and light colour, and even simulate weather. Occasional rain in the agricultural sections, variable humidity, the feel of moving air. They suggested including controlled wilderness areas where plant life grows in a semi-wild, semi-random state, because research consistently shows that exposure to unstructured natural environments reduces stress, improves cognitive function, and supports emotional well-being. A generation ship would need to carry not just humans but humanity itself, the full richness of landscape and sensation and randomness and surprise that makes biological life feel like life, rather than a laboratory experiment with no end date. You think about that as your body settles deeper into whatever surface is holding you right now. A wilderness area on a ship between the stars, a simulated forest in a tin can hurtling through the void, with artificial wind and artificial rain, and real trees growing in soil transported from a planet that the passengers' descendants will never return to. There is something achingly, stubbornly beautiful about it. The insistence on carrying nature into the unnatural, on refusing to let the journey strip away the things that make us who we are. The stars are cold and far away, but even in the space between them, someone would plant a garden. Someone always plants a garden. But what if you did not have to be awake for the trip? What if, instead of living through the centuries in a generation ship, watching your descendants carry the torch you lit, enduring the revolt of the middle generations and the recycled air and the absence of sky, you could simply close your eyes and skip the boring part. Go to sleep on departure day. Wake up on arrival day. The universe's longest nap. The ultimate expression of what you are already trying to do right now. Drift off and let time handle itself while you are blissfully unconscious and time passes without your participation. This is the concept of suspended animation, and it has been a staple of science fiction for so long that most people assume it is either already possible or fundamentally, permanently impossible. The truth, as usual, lives in the messy territory between those two extremes. We cannot freeze a human being, store them in a pod for centuries, thaw them out on the other side, and expect them to sit up and ask for coffee and a status report. But we are closer to slowing human biology down to a tall than you might think, and the research is advancing in ways that would have seemed like outright magic a few decades ago. Cryonics, the practice of preserving human bodies at extremely low temperatures after legal death in the hope that future science might revive them, is the most famous approach. Companies like Alcor Life Extension Foundation in Arizona have been cryopreserving clients since the 1970s, storing bodies in liquid nitrogen at -196 degrees Celsius, hoping future technology can repair both the cause of death and the freezing damage. The scientific community is deeply skeptical. Ice crystals shred cell membranes from the inside. More recent techniques use vitrification, replacing water with cryoprotectant chemicals that solidify into glass without forming crystals. Vitrification is better and works for small biological samples, but scaling it to an entire human body remains unsolved. However, there is a more scientifically grounded form of biological slowing that nature has been practicing for millions of years. Torpor. Bears hibernate, reducing their metabolic rate by 75%. Arctic ground squirrels drop their body temperature below freezing and survive. Hummingbirds enter torpor nightly. And here is the detail that makes biologists lean forward. Even some primates hibernate. The fat-tailed dwarf lemur of Madagascar enters hibernation for up to 7 months per year. Primates, our closest evolutionary relatives. If lemurs can do it, perhaps the genetic machinery for torpor is not entirely absent in the human lineage. NASA has funded real research into this. SpaceWorks Enterprises produced a detailed 2016 study on therapeutic hypothermia, carefully cooling the human body to about 32 degrees Celsius to reduce metabolic needs during long-duration spaceflight. At that temperature, metabolic rate drops by 50 to 70%. Astronauts in torpor would need less food, less water, less oxygen, and less physical space, fundamentally changing the economics of deep space missions. The technique already exists in hospitals. Cardiac surgery patients are routinely cooled to protect their brains during operations. The challenge for spaceflight is extending the duration from hours to months, and eventually years or decades, while managing the cumulative physiological effects of prolonged metabolic suppression. Historians still argue about the earliest cultural references to suspended animation. Some trace the idea to mythological sleeping heroes, King Arthur, slumbering in Avalon until Britain needs him again, Frederick Barbarossa, sleeping in a mountain cave, his red beard growing through a stone table, the 7 sleepers of Ephesus, who according to Christian and Islamic tradition fell asleep in a cave to escape Roman persecution and woke up centuries later to a changed world. Others point to more recent literary origins, Washington Irving's Rip Van Winkle in 1819, or H.G. Wells's The Sleeper Awakes in 1910, or the countless science fiction stories since then that have used cryogenic sleep as a convenient plot device for interstellar travel. The theme is ancient and universal across cultures, the desire to skip time, to leap forward, to avoid the tedium and suffering of waiting. It is, if you think about it, exactly what you're doing right now. Lying in the dark, trying to skip from wakefulness to morning, hoping the hours in between will pass gently without your conscious participation. Here is a quirky detail from the cutting edge of the field that might follow you into your dreams tonight. In 2020, researchers at the University of Tsukuba in Japan and Harvard Medical School successfully induced a torpor-like state in mice by stimulating specific neurons in the hypothalamus, a region of the brain involved in regulating body temperature and metabolism. The animals' body temperatures dropped significantly. Their metabolic rates plummeted, Their heart rate slowed to a fraction of normal, and they recovered fully and without apparent harm when the neural stimulation was removed. The neurons involved were in a specific cluster called the Q neurons, and intriguingly, similar neurons have been found in rats, animals that, like humans, do not naturally hibernate. The possibility, still highly speculative but no longer dismissible, is that the genetic and neural architecture for hibernation-like states may be more widely distributed across mammalian species than previously believed, including in species that never evolved the behavior naturally. If those dormant pathways could be activated in humans through targeted neural stimulation, genetic engineering, pharmacological intervention, or some combination we have not yet invented, then human torpor might not be a distant fantasy, but a latent capability, sleeping in our biology like a feature that was installed but never switched on. You smile at that, maybe, in the dark. The idea that the ability to sleep for centuries might already be coded inside you, written into your DNA in some ancient unused file, waiting patiently for someone to find the activation key. That the very thing you are doing right now, succumbing to drowsiness, letting your body temperature drop its nightly fraction of a degree, slowing your breathing and heartbeat as consciousness softly, willingly fades, is a faint, distant echo of a much deeper biological potential that your species simply never needed to activate on the warm savannas of Africa where we were born. You're already partway there. You're already practicing. The only difference between you and an interstellar cryonaut is ambition, about 180 degrees Celsius, and several centuries of technological development. For now, the small version will do. Close your eyes a little more, let the temperature drop, practice. There is one more trick the universe has up its sleeve, and it is stranger and more beautiful than anything human engineering has produced or is likely to produce for a very long time. It is built into the fabric of space and time itself, woven into the equations that describe reality at its most fundamental level, and it means that even though Alpha Centauri is 4.37 light-years away, for everyone watching from Earth, it might feel like considerably less for the person actually making the trip. This is time dilation, and it is one of the most counterintuitive, experimentally confirmed, and emotionally devastating consequences of Einstein's special relativity. Remember the speed of light problem from several sections ago? Nothing with mass can reach the speed of light, and as you approach it, strange things begin to happen to the fabric of your experience. One of the strangest is that time itself slows down for you relative to everyone you left behind, not in a vague, philosophical, poetic sense, in a literal, measurable, experimentally confirmed to many decimal places sense. The faster you move relative to someone else, the slower your clock ticks compared to theirs. At everyday speeds, driving, flying, even orbiting the Earth in the International Space Station, the effect is absurdly tiny, measurable only with atomic clocks of extraordinary precision. But at significant fractions of the speed of light, it becomes dramatic enough to change the entire calculus of interstellar travel, and, more quietly, to break your heart. Here are the numbers. At 50% of light speed for every year on your ship, about 1.15 years pass on Earth. At 87%, the ratio doubles. At 99%, it is 7-to-1. At 99.9%, roughly 22-to-1. At 99.9999%, over 700-to-1. 1 year of your experience while 7 centuries pass on Earth. The closer you get to light speed, the more aggressively your personal time compresses, as though the cosmos was squeezing your timeline like an accordion. So what does this mean for a trip to Alpha Centauri? if you could somehow accelerate to 90% of the speed of light and maintain that speed for the journey, the trip from Earth's perspective would take about 4.86 years, slightly longer than the 4.37 light-year distance would suggest, because you are moving fast but not quite at light speed. But from your perspective, aboard the ship, thanks to time dilation, only about 2.1 years would pass. 2 years and change. You could leave Earth, read a shelf of novels, maintain a workout routine, learn to play the guitar badly, and arrive at Alpha Centauri with your body having aged barely 2 years. From your subjective point of view, the universe literally shortened in the direction of your travel, a phenomenon called length contraction, the spatial counterpart to time dilation. At 90% of light speed, the 4.37 light-year distance looks like about 1.9 light-years to you. The universe cheats in your favour, squishing space and stretching time so that the experience of travelling near light speed is profoundly, measurably different from the experience of watching someone travel near light speed. You and the people you left behind literally inhabit different versions of elapsed time. There is a classic thought experiment, the twin paradox. You have an identical twin. You fly to Alpha Centauri at 90% of light speed and come back. Your twin waits on Earth. From their perspective, the round trip takes about 9.7 years. They age a decade, their hair greys a little, they get promoted, they adopt a dog. From your perspective, only about 4.2 years have passed. When you step off the ship, you are genuinely, physically younger than your twin by 5.5 years. Not because of some perceptual trick, but because time actually passed more slowly for you. Your atoms vibrated fewer times, your heart beat fewer beats, your cells divided fewer times. You are, in every measurable sense, younger than the person who shares your exact DNA. This is not theoretical speculation. It is confirmed experimental fact. In 1971, physicist Joseph Hafele and Richard Keating bought commercial airline tickets, flew atomic clocks around the world in both directions, and compared them to identical clocks that stayed on the ground. The flying clocks were off by exactly the amounts relativity predicted, a few hundred nanoseconds, measured with exquisite precision. Today, GPS satellites experience time dilation amounting to 38 microseconds per day. If GPS software did not correct for this, your navigation would drift by 10 kilometers daily. Every time you use your phone to find a restaurant, you're relying on Einstein being right. Historians still argue whether Einstein anticipated the practical implications when he first described time dilation in 1905. Here is the bittersweet part, and this is the detail that tends to land with particular weight at night, in the dark, when your emotional defences are lowered and the universe feels very large and very quiet. Time dilation helps the traveller. It compresses their experience, shortens their subjective journey, makes the impossible merely very long. But it devastates everyone left behind. You fly to Alpha Centauri and back in what feels to you like 4 years. But when you land back on Earth, nearly 10 years have passed. Your friends have aged a decade. Your children, if you had children, have grown. The dog your twin adopted has grey in its muzzle. The world has moved on without you, not because you were gone a long time by your own reckoning, but because the universe ran 2 clocks at different speeds and yours was the slow one. The faster you travel, the worse this asymmetry becomes. At 99% of light speed, a round trip to Alpha Centauri takes about 8.8 years on Earth, but only about 1.3 years for you. You come back barely older, to a world that has aged nearly a decade, full of people whose lives continued at full speed while yours was compressed into a thin sliver. You lie there and you feel the weight of that thought. The universe offers a discount on distance, but the price is disconnection. You can skip the years, but you cannot bring the people you love with you through time. The stars are reachable, at least in principle, but the people you leave behind are not. And as your eyelids grow heavier and the night grows deeper, that feels like the most human thing about physics, that even the fundamental laws of the universe involve trade-offs and compromises, and the quiet ache of things left behind. Say you make it. Against all odds, against the vacuum and the radiation and the distance and the physics and the engineering and the budget, you get to Alpha Centauri. You are there, you have arrived. You look out the window of whatever vessel carried you across the void, a generation ship, a torpor pod, a laser-pushed nanochip with a camera the size of a fingernail, and you see it. 2 bright stars waltzing in their 80-year orbit, close enough to show as disks rather than points. A dim red dwarf flickering somewhere in the distance. Maybe, just maybe, a rocky planet with a permanent twilight zone, sitting in the habitable zone of that moody little star. You have done it. Humanity's greatest journey, measured not in footsteps or nautical miles but in light years. And the very first thing you want to do, naturally and irresistibly, is tell someone back home about it. You open a communication channel. You compose a message, something historic, something worthy of the moment, something that will be carved into monuments and quoted in textbooks. We made it. Alpha Centauri is beautiful. Send pizza. You press send. The message leaves your transmitter at the speed of light, the fastest it can possibly travel, the absolute cosmic maximum, and then you wait. Because that message, hurtling homeward at 299,792 kilometers per second, will take 4.37 years to reach Earth, and if they reply immediately, which they will not, because bureaucracies and committee meetings and funding review boards exist even in the glorious future, the reply will take another 4.37 years to reach you. Total round-trip communication time for a single exchange, 8.74 years. Nearly a decade for one question and one answer. Your conversation has the responsiveness of a particularly lazy pen pal who also happens to live in a different geological epoch. This is the communication problem, and it is just as fundamental as the travel problem. The speed of light caps not only matter but information. Every signal, every method of transmitting data that does not violate known physics is limited to 299,792 kilometers per second. No exceptions, no loopholes. What about quantum entanglement? 2 particles, entangled, sharing a quantum state so that measuring one instantly affects the other regardless of distance. Einstein called it spooky action at a distance. Surely you could use it for faster-than-light messaging. The answer is no. When you measure one entangled particle, the result is random. You cannot control it. The correlation only becomes apparent when you compare measurements from both ends, which requires a classical channel limited to light speed. Entanglement is a correlation, not a communication link. Like 2 coins that always land on opposite sides, but you cannot choose which side yours lands on. Historians still argue whether future physics might change this, but current consensus is firmly against it. So you are stuck with light-speed communication, and that means every interaction between Alpha Centauri and Earth becomes a long, slow, melancholy exchange of monologues, rather than anything resembling a conversation. You send a status report. All systems nominal. beginning atmospheric analysis of Proxima Centauri b. Weather here is non-existent. 4 years and 4 months later, Earth receives it. They celebrate. They hold press conferences. They compose a reply. Incredible work. Whole planet is cheering. Here is an updated software patch and a recording of your daughter's college graduation. She says she misses you. 4 years and 4 months later, you receive it. Your daughter graduated nearly 9 years ago. She is now married. She has children you have never met, whose faces you will not see for another 4.37 years after someone thinks to send a photograph. The emotional weight of that delay, the sheer accumulating sadness of a relationship stretched across light years, is as staggering as the physical distance that causes it. Here is a thought to turn over as the night deepens. If a colony were established at Alpha Centauri, the two populations would effectively become separate cultures within a generation. News, music, politics, language, all would drift apart because the feedback loop that keeps communities synchronized would be useless across a 4.37-year delay. Within decades, they would be culturally distinct. Within centuries, as different as Rome and Han Dynasty China, the colony would not be an extension of Earth. It would be a new humanity, born under alien light. This has precedents in human history, and they are instructive. The Polynesian settlers who reached Hawaii, New Zealand, and Rapa Nui, Easter Island, became, over centuries of isolation, distinct cultures so different from each other and from their ancestors that only genetic and linguistic analysis can fully trace the connections. The colonies that Europeans established in the Americas developed their own identities and eventually their own national characters within a few generations, eventually fighting wars of independence against the parent cultures that spawned them. Distance breeds difference, and the distance between star systems, measured in years of light-speed delay, makes the Pacific Ocean look like a creek you could step across on a dry day. You think about that as the night presses gently on your eyelids, the loneliness of it. Not just the physical isolation of being 4.37 light-years from everyone you know, but the temporal isolation, the knowledge that every word you send is already ancient history by the time it arrives, that every reply you receive is a ghost of a conversation that happened years ago, that the people you love are living their lives on a clock you can no longer share, and yet, and this is the part that catches in the throat like an unexpected emotion, you would still send the message. Humans have always sent messages into the dark, knowing the reply might never come or might come too late to matter. We wrote on cave walls knowing we would not live to see who read them. We buried time capsules knowing we would not be there for the opening. We launched the Voyager Golden Records into interstellar space, carrying greetings in 55 languages, music from Bach to Chuck Berry, images of life on Earth, whale songs and thunder, and the sound of a mother's heartbeat, addressed to no one in particular, on a journey that will outlast our civilization by millions of years. The impulse to reach out, to say, I am here, I existed, I mattered, transcends the speed of light, not physically but spiritually, because it was never really about the reply. It was always about the sending. So why? You have heard the distances. You have felt the weight of the numbers pressing down on your consciousness like a warm, heavy blanket. You know that the nearest star is a billion-year walk, a 73,000-year Voyager drift, a 20-year laser shot that requires technology we do not yet possess. You know that communication would be agonizingly slow, that any colony would become a separate civilization within generations, that the void between here and there is an almost perfect vacuum dotted with invisible radiation. You know all of this, every discouraging detail, every sobering calculation, and yet, why does the dream persist? Why, after everything, do humans keep pointing at the stars and saying, with seemingly irrational confidence, "Let us go there"? The easy answer is curiosity. Our ancestors who wandered, who crossed the next ridge, forded the next river, sailed the next stretch of ocean, found new resources and new advantages. The ones who stayed put were more vulnerable. Natural selection rewarded the restless. We are the descendants of the curious ones, and that restlessness is encoded in our neurobiology, wired into dopaminergic circuits that release pleasure when we encounter novelty. You're neurochemically incentivized to find the unknown appealing. It is not entirely a choice. It is biology whispering across 100,000 generations, "Go look, there might be something good over there." But the deeper answer is harder to articulate, and it is the one that keeps philosophers and poets and late-night thinkers awake long after the scientists have finished their calculations and gone to bed. There is something about the human relationship with distance and the unknown that transcends survival, calculus, and reward chemistry. We do not explore only because it is advantageous in a Darwinian sense. We explore because we find meaning in the act itself, because the journey matters independently of the destination. And yes, I know that sounds like something printed on a motivational poster in a dentist's office, but it also happens to be true in a way that motivational posters usually fail to capture. Consider the history of exploration on this planet. The Polynesian voyagers crossed thousands of kilometers of open Pacific in double-hulled canoes. Why? They had perfectly good islands already. They were not fleeing disaster. They sailed into the unknown because their culture valued the act of sailing into the unknown. Shackleton's Antarctic expedition served no practical purpose. Hillary and Tenzing climbed Everest for no reason other than Mallory's answer: because it is there. That phrase is the most honest justification for exploration ever spoken, and it applies to Alpha Centauri as surely as it applied to a mountain in Nepal. Historians still argue whether the urge to explore is cultural or universal. The evidence suggests both. A universal trait each culture expresses differently, like music or language. There is also the survival argument, and it is more urgent than it sounds. Right now, every human being who has ever lived is on a single planet. One sufficiently large asteroid, and we know these happen because the dinosaurs are not here to argue otherwise. One supervolcano, one pandemic, one nuclear exchange, and the story of humanity ends. Not a chapter, the whole book. Every sonnet Shakespeare wrote, every theorem, every painting, every love letter, every memory of every person who ever existed, gone irretrievably, because we kept all our eggs in one basket and the basket broke. Becoming a multi-star species is not just a romantic adventure, it is an insurance policy. The difference between a civilization that can be ended by a single catastrophic event and one that endures regardless. Carl Sagan articulated this most powerfully in his 1994 book Pale Blue Dot, reflecting on the famous photograph of Earth taken by Voyager 1 from a distance of 6 billion kilometers. In that image, Earth is a tiny speck, less than a single pixel, suspended in a scattered beam of sunlight. Sagan wrote, with the quiet intensity that was his trademark, that every person you have ever heard of, every human being who ever was, lived out their entire lives on that mote of dust suspended in a sunbeam. The image is humbling beyond anything words can fully convey, and the implication is luminously clear. If that mote of dust is all we have, and it is fragile and it is temporary, and it floats in a universe that is vast and mostly empty and largely indifferent to our survival, then reaching for the stars is not a luxury or a hobby for dreamers. It is a necessity. It is the most important thing we could possibly do. Here is a quirky, endearing, perfectly human detail that captures the spirit of why we try even when trying seems absurd. In 2015, a group of artists and scientists at the Massachusetts Institute of Technology created a project called A Space Between Us, in which they launched a helium balloon carrying a small capsule to the edge of near space, approximately 30 kilometers above the Earth. Inside the capsule were handwritten poems, personal letters, and small objects contributed by strangers from around the world. A wedding ring, a child's drawing, a pressed flower, a photograph. The capsule reached the stratosphere, hung there for a while against the black of near space with the curved blue edge of Earth below it, and then fell back down. It did not reach Alpha Centauri. It did not even leave the atmosphere. But the act of sending human words and objects upward toward the stars, even symbolically, even knowing it would come right back, felt meaningful and real and necessary to every single person who participated. We reach because reaching is who we are. The distance is, in a sense, irrelevant. The direction is everything. You feel that now, in the quiet. The same ancient impulse that made your ancestors walk out of Africa and across every continent, sail every ocean in boats made of reeds and animal hides, climb every mountain just to see what was on the other side. The same impulse that has you lying here at this hour, listening to a voice describe a star system 41 trillion kilometers away, instead of sensibly closing your eyes and forgetting about it. You cannot help it. You're wired for this. You are, in the deepest and most ancient sense of the word, a traveller. And Alpha Centauri is just the next horizon, impossibly far and irresistibly bright, like every horizon that has ever drawn a human being forward into the unknown and the uncertain and the beautiful. And now the journey softens. The numbers fade gently, like colours at the end of a sunset bleeding into grey, and then into the deep blue black of night. The propulsion systems and the light years and the particle physics and the communication delays all begin to blur at the edges, like a watercolour painting left out in a warm, gentle rain. You are still lying here, wherever here is. Your bed, your couch, a hammock, the floor of a room that smells like nighttime and clean sheets, and something faintly sweet you cannot quite identify. The stars are still above you, even if a ceiling separates you from them. Alpha Centauri is still 4.37 light-years away. That has not changed. It will not change tonight, or tomorrow night, or any night in your lifetime. But something else has shifted, something quiet and internal. The distance no longer feels like a wall. It feels like a horizon, and horizons, unlike walls, are invitations. You have travelled, tonight, across the full span of that distance in your mind. You have walked it, and driven it, and surfed nuclear explosions and dreamed of antimatter engines. You have imagined generation ships where someone plants a garden between the stars, slept through centuries in a torpor pod, and felt time dilate around you like honey off a spoon. You have sent a message home that would not arrive for 4.5 years. You have done all of this without leaving the place where you're lying right now. The distance between here and Alpha Centauri is 41 trillion kilometers. The distance between your imagination and Alpha Centauri is 0. Think about what you carry into dreams tonight. Not just the facts, but the feeling of smallness that is somehow liberating. If the universe is this large, then the email you forgot to send does not matter tonight. The deadline, the bill, the argument, none of it registers at interstellar scales. You are atoms on a mote of dust, and the nearest star needs 4 years of light-speed travel to reach. Your problems are real. Your feelings are valid. But against 41 trillion kilometers, they are also mercifully small. Small enough to set down, small enough to leave at the door of sleep. Remember the 3 stars. Alpha Centauri A, warm and yellow and almost identical to our sun, spinning in its 80-year waltz with its partner like 2 old dancers who've been moving together so long they no longer need to count the steps. Alpha Centauri B, cooler and quieter, a gentle orange companion, the reading light star, the one that does not demand attention but rewards it. And Proxima, the little red dwarf, distant and moody, flickering with flares that would strip worlds bare, yet somehow endearing in its fierce stubbornness, the smallest star in the nearer system, refusing to be overlooked, refusing to be ignored, tossing its tantrums into the void like a child who knows that even negative attention is still attention. They have been there for 6 billion years. They will be there for billions more. They are not waiting for you. They are not aware of you. But they are there, constant and patient in a universe that is mostly dark and mostly empty and mostly silent, and their light reaches you every single night, whether you look up or not. That continuity, that quiet, ancient, unhurried persistence, is the last thought worth carrying with you into the dark. The pillow is soft if there is a pillow. The grass is cool if there is grass. The hum of the world around you, traffic, crickets, a refrigerator, a fan, has resolved into a single steady tone, like the cosmic microwave background itself, the leftover whisper from the Big Bang, still murmuring through every cubic centimetre of space 13.8 billion years later. Everything is old, everything is far away, and everything is exactly where it should be. You do not need to reach Alpha Centauri tonight. You do not need to solve the propulsion problem, or the communication problem, or the generation ship problem, or the antimatter production problem. Those problems belong to tomorrow, and to the tomorrows after that, and to the species, whatever that species calls itself by then, that will eventually solve them. Tonight, you just need to close your eyes. You just need to let the distance carry you, not toward the stars, but towards sleep, which is its own kind of voyage, a journey inward, to a place even more mysterious and less mapped than the interstellar void, where dreams are assembled from the raw material of everything you have ever experienced, everything you have ever wondered about, including, now, the knowledge that the nearest star is 4.37 light-years away, and that someone, someday, will cross that distance and stand in the light of another sun and think of home. Your breathing has slowed to the rhythm of something ancient and involuntary. Your heartbeat has softened to a murmur. The words are growing quieter now, like a voice heard from the next room, then from down the hall, then from somewhere far away and gentle, and the spaces between the words are lengthening and deepening, becoming part of the silence rather than interruptions of it. The stars are up there, Alpha Centauri is out there, and you are right here, warm and heavy and drifting, suspended in the dark the way a planet is suspended in space, held in place by forces you do not need to understand in order to trust. The distance between all these things is exactly as large as it needs to be. Not too much, not too little. Just enough to remind you that you are part of something vast, and that being small within it is not a weakness, but a kind of grace. Sleep now. Let the light years pile up around you like soft, heavy blankets, one on top of another. Let Proxima Centauri flicker without you. Let the Oort cloud guard the solar system's dark edge, while you guard nothing at all just for these few hours. Let the void be vast and the silence be deep and the distance be whatever it needs to be. The universe is not going anywhere. The stars will keep their ancient, patient positions. And you ancient, curious, restless, wondering, dreaming creature, you will wake up tomorrow, and the first thing you will do, probably without even thinking about it, is look up. Sweet dreams.